But we need to know where we're going and how we're going to get there, and that's what David's going to tell us about tonight. So David has been studying Apollo samples. I presume that means moon samples and not astronauts. He's been studying Apollo samples for more than 3 decades, learning about asteroid bombardment, volcanic processes that shape the lunar surface, and he leads a large team helping NASA develop an architecture for long-term exploration and utilization of the lunar surface. He's trained astronauts on how to work on the lunar surface and on planetary surfaces in general. He's developed concepts of human-assisted lunar sample return missions and a whole range of other things. As I mentioned before, he's a really well-known speaker. LPI is a great organization locally, and it's a great pleasure to welcome David tonight. Thank you.
Okay, thank you. Oh, we have a full room. I had to turn it around. So very glad to be here and have the opportunity to say something about the lunar South Pole and some of the ideas that we are working on for the 7th landing, which is scheduled for 2024. That's just a little bit more than 4 years from now. Okay, so we're on a very fast track. There's a lot of late nights and weekends in everybody's schedule right now. Before I talk about the lunar South Pole, however, I want to say something about Apollo and what it is that we learned from Apollo. One of the lessons is that the moon is just a geologic wonderland. It is one of these places in the solar system that has an exquisite geologic record that not only informs us about the moon, it informs us about the Earth, it has the capability of informing us about the origin and evolution of the entire solar system. It really is a magical place. But the other point that I want to make is most of what we've learned comes from the samples that the astronauts collected and returned to Earth. We've had some fantastic missions that fly by and orbit the moon. The Big Bang, if you will, from the science perspective, usually has come from these samples. So it's generated a lot of what I call big ideas, those samples. Based on the samples that the Apollo astronauts collected, we had revised our ideas for the origin of the moon. We now understand that the Earth-Moon system probably has its origin in a giant impact between 2 primordial bodies. We still debate the velocity of that collision and the size of the objects, but nonetheless it was a very giant impact. Based on the lunar samples, we've developed a lunar magma ocean hypothesis that posits that the moon was once surrounded by an ocean of magma that eventually crystallized to form the moon that we see today. After that moon solidified, it was severely bombarded by impacting asteroids and comets, perhaps 500, 600, 700 million years after solar system formation, probably due to the orbital migration of Jupiter and Saturn. That bombardment seems to be intimately associated with the origin and early evolution of life on our planet and potentially Mars. We understand that one of the largest impact events on the lunar surface, the South Pole Aiken Basin impact event, and I'll say something more about that in a few more minutes, may have actually generated a huge pulse of magmatism on the near side. In fact, may be responsible for a lot of the volcanic rocks that the Apollo astronauts collected. And more recently, we've come to understand, as new analytical techniques have improved, that there actually are traces of water on the moon, and that actually may be very important to our future exploration, as I'll speak in more detail in a moment. Okay. So putting all that together, we have this new picture of the early evolution of the moon. Here it is after the giant impact event as a large molten object. The crust is beginning to solidify as it cools. In a moment, you'll see a large asteroid producing the South Pole Aiken Basin. That's on the far side of the moon. And after its debris had settled to the lunar surface and some period of time had passed, maybe 100 million years, maybe 200 million years, there was a flurry of asteroids and a few comets hitting around 4 billion years ago. Okay, so that's what Apollo gave us. Apollo provided just a few hours on the lunar surface to just a few locations on the lunar surface. I was pointing out to David that the area explored by the Apollo 11 astronauts is not much larger than the Quad here at Rice University. It's a really tiny area of the moon that's explored. So about a decade ago, we started 6 years of summer studies to evaluate where on the lunar surface we should go if and when we did return to the lunar surface to address these big ideas and to push forward the frontiers of our knowledge of solar system processes. And at the top of the list came the Schrödinger Basin. This is 320 kilometers in diameter. It's on the far side, so we're looking from the far side over the South Pole. Here you see the Earth in the distance. If we were to go back purely for scientific purposes, this is undoubtedly where we would go. After that 6-year study, we spent another 6 years designing landing sites for astronauts and some traverses. Here, for example, is one of the prime landing site locations. These are such high fidelity studies, we've already identified some of the rocks that we want them to pick up. Okay, however, that is if we were going back simply to explore for scientific reasons. However, in that same interval, we became increasingly sensitive to the fact that the moon did contain some water, and that some of that water may have been transported across the surface of the moon and deposited in caches that are recoverable. And so the idea has grown that we might be able to harvest that water, provide consumables for crew, provide water, which is a very good shield for radiation, and provide propellant for activity on the lunar surface and to carry astronauts deeper into the solar system. Okay, so with that perspective, we have been pushed from an attention here in the Schrödinger Basin towards the South Pole, and the Vice President articulated this clearly in about 10 months ago. He said to reach the moon in the next 5 years, we must select our destinations now. NASA already knows that the lunar South Pole holds great scientific, economic, and strategic value, but now it's time to commit to go there. And so we are going there. 2024 is our target date, and the South Pole is our target landing site. So I'm going to focus the rest of the presentation on what we know about the lunar South Pole. Okay, now, again, the reason we're being pushed towards the South Pole is in part due to volatiles. This is a volcanic vent in the floor of the Schrödinger Basin. This happens to be the largest indigenous source of volatiles in the South Polar region of the moon. When that volcanic vent was erupting, it was spewing mostly carbon monoxide and carbon dioxide, but it did carry substantial amounts of water. Once those volatiles reached the surface, they had the capacity to hop and be transported in all directions, but those components that did travel towards the South Pole could be trapped there by very, very cold temperatures. And I'll explain in a moment why those cold temperatures exist there. So, with that knowledge, NASA has developed a plan. It's called the Artemis Program. I'm going to show you 2 charts that outline the plan as it exists today. The first chart is Artemis Phase One. This is from 2020 to 2024. The first mission is Artemis 1. This used to be called Exploration Mission 1. This is going to carry the Orion crew vehicle around the moon and return it to Earth. Artemis 2 is going to carry astronauts around the moon and return them to Earth. And then there's going to be a series of flights that build a orbiting asset that's currently called the Gateway above the lunar surface. And then in 2024, we'll have Artemis III, which will carry crew to the Gateway, and then from there they will descend to the lunar surface at the South Pole. At the moment, the capability is, or the plan is to carry 2 astronauts, the first woman and the next man to the lunar surface at the South Pole. After that landing occurs, then there will be a series of additional Artemis missions, and a growing and expanding capability on the lunar surface. We actually should have several surface missions with crew before 2029 or before the decade is over. Now, these missions, certainly Artemis III, landing at the South Pole, is going to establish an outpost on the edge of the largest impact basin on the lunar surface and arguably the largest basin in the solar system. It is called the South Pole Aiken Basin because its diameter spans from the South Pole 2,500 kilometers to the small crater called Aiken. It's 13 kilometers deep, so it is an absolute monster. So, you know, this is a good size structure relative to the United States and North America. It is quite immense. If we take a closer look at the South Pole, it is located right here. It's on the rim of Shackleton Crater. We're going to be talking a lot about Shackleton Crater here this evening. This is a 20 kilometer diameter impact crater. And you'll see it's a simple crater. That is, it's a nice bowl-shaped crater, almost a perfect bowl-shaped crater. The Earth is in this direction. The far side is in this direction. That is the limb of the moon as seen from the Earth. So if you're on this side and peering in this direction, if there wasn't a couple of big mountains here, you could actually see the Earth. One potentially has direct communication with Earth from locations in this region. But again, there is tremendous topography here that is going to impede some of the communication. Shackleton Crater is, as I said a moment ago, a simple crater, much like Meteor Crater in Arizona. And so I want to show you a picture of Arizona's crater in just a moment. But for those of you who don't know how an impact crater forms, we've put together a little model. This is a computer simulation. This black line represents the topography of Shackleton Crater as it is measured today. We're going to reproduce this impact crater with a 1.5 kilometer diameter asteroid hitting at 15 kilometers per second. And let's watch. Crater forms in about 5 or 6 minutes in real time. And you can see that the simulation mimics the topography quite well. There's a fascinating story as to why it doesn't match over here, and I can't tell you about that because it's under review in a prominent scientific journal. What the code does tell us is that the impact produces about 150 meters of impact ejecta on the rim. Okay? So if astronauts are deployed on the rim of Shackleton Crater, they're going to be landing on and working on rubble. That's something that they're familiar with, for those that have trained at Meteor Crater, because just like Shackleton, it's surrounded by impact ejecta or a rubble deposit. So this is Meteor Crater in Arizona. It is a kilometer or 1.2 kilometers across. It's 180 meters deep. There is a rim that's uplifted relative to the surrounding landscape. That's actually uplifted by the impact event. And all of this material that you see surrounding it is material that was ejected from the crater by the impact event. So the same type of material is going to be encountered at Shackleton Crater. As I said before, this is a perfect analog for craters on the lunar surface, and for that reason, it was a prime training site for astronauts during the lunar program, and we still use it to train astronauts today. For those of you who are not going to get to go to the moon, if you want to see what it's like on the moon, I invite you to go to Meteor Crater. It's a wonderful place. It is the world's best preserved impact crater. There's actually one of the Apollo test capsules there. It's actually a wonderful place to visit. Okay.
Gene Shoemaker?
This is Gene Shoemaker, yes, with some of the Apollo astronauts. Let's see. Okay. There is a big difference.
and that's size. So Meteor Crater is 1.2 kilometers across, Shackleton is about 20 kilometers across, okay, and that's a big number. To give you some sense of scale, I've put the highway road system of Houston on top of a picture of Shackleton. Okay, here's the Space Center down here. We're sitting here at Rice University. There's 610, there's the 8 Beltway, and so the next time you have a mind to drive all the way around 610, okay, just picture yourself driving all the way around Shackleton Crater, okay? Less traffic on the moon, yeah. But you're not going to be able to go quite so fast, I think. Okay, not only is the diameter large, it's also very deep. Okay, so here is a cross-section of Shackleton Crater. It is over 4 kilometers deep, and if you're having a mental breakdown on how to picture that, well, if you've been to the Grand Canyon, it's 3 times deeper than the Grand Canyon. Okay, so again, if you're wanting to get a sense of what it's like on the moon, I invite you to go to the Grand Canyon. And while standing on the rim, imagine a structure over 3 times deeper. Okay. Now, the illumination conditions at the South Pole are very interesting. So at the Apollo landing sites, you know, the sun rises on the east, it goes overhead, it sets in the west, just like on the Earth, where we are here in Houston. But at the poles, the sun hovers along the horizon, okay, just a few degrees around the horizon. It may bob up and down. Every once in a while, it's low enough around the horizon, it actually disappears behind a mountain range, okay? So the sun is just going around in a circle, okay? And it's going to be casting these large shadows wherever there's topography, like Shackleton Crater, okay? So a structure as deep as Shackleton Crater is going to have a portion of it that never sees the sunlight. Okay? It is in permanent shadow. We call these permanent shadowed regions, and they are exquisitely cold. Okay? These are the types of places where you want to do your physics experiments at near 0 Kelvin. Okay, so this is an illumination map of the Shackleton area. Here's Shackleton. The South Pole is right there. And you can see how the shadows work themselves around Shackleton. So there's a couple of things to keep in mind if you are thinking of operations on the lunar surface. That first, you have this dramatic topography that I've been describing, far greater than anything that we're used to working here on Earth. It casts these long shadows. In some sense, they're unpredictable. They're not intuitive as to where those shadows would be because they are so long. They're very deep shadows, as it said, these permanently shadowed regions, or PSRs. And in stark contrast are a few small, near constantly illuminated areas. If you look really closely, there's a couple of places that never quite go dark, or go dark only very briefly. And here's a map of those locations. Here's Shackleton again. Here, 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 and here. These are 4 highly illuminated areas. One on the rim of Gerlach Crater, Shackleton Crater. One on this ridge between Shackleton and Gerlach. And there's a plateau over here where there's another one of these sunlit regions. Those are important for solar energy or for power. Okay? Now, we're very interested in going there and harvesting that power, but I have to say that there's still a need or a method for distributing that power elsewhere where we might want to use it. Okay, let's say something more about those cold temperatures. So this is a thermometer. Here's absolute 0. So this is 0 Kelvin. Okay, up here is 300 Kelvin. Freezing point of water, 273 Kelvin. Here we have the average temperature of Pluto, 40 Kelvin. Okay, the coldest annual average temperature on the moon is lower than that. Okay, even though we're considerably closer to the sun, it's actually lower than that in these PSRs. And the lowest recorded temperature on the moon is way down here at 23 K. Okay? Now, the lunar surface is a vacuum. It's an airless body. And so when we talk about the stability of volatile constituents, we have to talk about them in terms of their sublimation points. The sublimation point of water is 107 Kelvin, ammonia 66 Kelvin, carbon dioxide, I somehow magically cut the number off, and argon's way down here at 20K. But you can see that for a lot of the temperatures that we might have in the polar regions of the moon, these types of volatile elements actually may exist in ice form. And that's what we're after for. That's what we're prospecting for. Okay, so why is water ice important? I said this before, because it can be used for crew consumables, water and oxygen. It's a wonderful radiation shield, and it can be utilized as rocket propellant. Okay, so what's the source of that water? There's three basic sources. The first is it can be delivered by impacting asteroids and comets. Okay, comets, that's easy. Everybody thinks of them as water-rich bodies. They're roughly 50% water ice. And asteroids are oftentimes thought of as just rocky objects, and that is largely true. But even the rockiest have a few percent water. And carbonaceous chondrites, a very common type of asteroid from the outer portion of the asteroid belt, can have 20% water. Okay, so for the astrophysicists in the room, 20%, 50%, same order of magnitude. Okay, so wet asteroids are not that different from comets. And early in lunar history, remember that period of bombardment that I tried to illustrate in that movie? A lot of water was being delivered to the lunar surface between 3.8, 3.9, 4, 4.2 billion years ago. Okay? So very important source at that time. Another important source is the volcanism that occurs on the lunar surface. Now, I have to say that we have a false sense of how much volcanism there is on the lunar surface because a lot of it is concentrated in the equatorial region of the moon. Okay? What you may not appreciate is because the moon is a sphere, the apparent surface area of that area, region covered by volcanism, appears very large, even though it's only about 17 or 18% of the lunar surface. Okay? So there was volcanism. It was very important, but it's not as important as we sometimes think when we see these dark mare from our backyards. But anyway, there was a couple of periods, about 3.8 billion years ago and 3.5 billion years ago, where the volcanism was so intense, it was venting volatiles to the surface quicker than they could escape to space. And so there actually were periods of a transient atmosphere around the moon. So think about the moon with an atmosphere, which you see pictured here. Okay? So at 3.5, 3.8, volcanism was providing some of the volatiles. And throughout the entire history of the moon, we have the solar wind occurring. So for those of you who don't know, the solar wind is this plasma that contains ions of electrons, contains ions and electrons in a magnetic field. It gets roaring across the solar system. It hits lots of objects, including the moon. The solar wind delivers hydrogen, helium, carbon, and nitrogen, and some other constituents. So that has been active throughout solar system history and continues to deliver volatiles to the lunar surface today. So if you were looking at an ancient crater with an ancient cache of ice, it may be dominated by volcanic sources and impact sources. But if you're looking at small or very young icy caches, it's probably dominated by volatiles delivered by the solar wind. Okay, now where are those deposited? Here, I want you to focus on this side of this chart. This is the annual maximum temperature that's plotted. And here's Shackleton Crater. There's our South Pole. And this is a scale bar from 120 Kelvin to 50 Kelvin. Water ice is stable. Well, the sublimation temperature is down here, and it's going to be very stable down here. So anywhere you see these colors, red to blue, are places where water ice can exist. In the coldest regions, the blue regions, it may be right at the surface. In these warmer regions, it may just be a few centimeters beneath the surface. But potentially, there is water ice that can be harvested from all of those regions. That's actually quite a large area. Okay? And so that's what's drawing us to the South Pole. Now, these are these are measured temperatures, And then there are model calculations for the stability of water ice, but we do have some evidence that it does exist there. And I want to show you 3 lines of evidence. The first is we have detected from orbit hydrogen. This is a hydrogen map, so all of these areas that you see blue have anomalous abundances of hydrogen. Okay? And hydrogen can react with oxygen in the regolith and produce water. So that's a hint that water ice may be there. And you can see that these blue patches correspond to those cold predicted regions of water ice in the previous chart. We also had an impactor experiment in 2009. That is, we flew a spacecraft into the lunar surface, into one of these suspected white icy patches, and that cratered the lunar surface. It threw up debris, as all cratering events do, and then the cone of debris was imaged by spectrometers, and the molecular lines from molecular hydrogen, H2S, CO, CO2, ammonia were detected in that plume. So we have a measurement of volatiles ejected from the surface of the moon. And most recently, just in 2018, again using orbital spacecraft, all of these blue dots represent areas where the spectra of water has been observed within the uppermost few millimeters of the surface. Okay? So we have hints that the models are correct. Now, what we have to do, of course, is to land and actually test these models in situ, either robotically or with crew. So let's imagine we've launched our astronauts. They're approaching the moon, and they are now approaching the lunar South Pole. And let's spend now a few more minutes talking about what they actually might be able to do or accomplish on the lunar surface. Okay, so again, to get you located, here's Shackleton Crater. Okay, all right. So imagine they go into orbit and they then descend to the lunar surface, and we're asking ourselves, what is it that they might do? And that's actually a question we want to answer now, as opposed to after they land. Okay. All right. So let's go back to our map. You've seen this before. There's the South Pole. Okay. South Pole right there. There's Shackleton Crater. Now, to accurately describe surface activities, the location of the landing site needs to be known. Okay? But at the moment, the specific landing site in the South Polar region has not been selected. Okay? But to illustrate what options they may have, let's say they're going to land somewhere along the rim. Okay? And then after we talk about that, we'll focus on the South Pole more precisely. Okay? So here's the South Pole. There's the rim. So let's imagine they're going to land somewhere on the rim. By the way, this dark shadow line, that's the edge of the permanently shadowed region. If you go lower than that into Shackleton, you're in permanently shadowed territory. And we do believe there's water ice down here on the surface. Okay? Now, here I have plotted using elevation, measured elevation on the lunar surface, the areas where we think the topography is going to permanently shade the surface from the sun. So everywhere you see these dark patches, in addition to Shackleton, all these small areas may be very small permanently shadowed regions. Okay? So potentially, if an astronaut is working along the rim, this ridge, at the base of this ridge, they could potentially test our ideas of volatile presence or absence by sampling that material. Now, this is something, by the way, that was done during Apollo. On both the Apollo 16 and 17 missions, the geologists identified locations that we thought had been in shadow for 10, 20, 30 million years, and they were asked to sample that material. So this is Charlie Duke taking a picture of John Young, who's sampling 63320. Okay, so we've been into these types of small territories before, and so this is something that we know how to do, and we can do it again. Okay. Also, some volatiles, if not at the surface, may be just below the surface. This is a calculation of ice stability depths by Matt Ziegler. In red, or white here, in red means they're right at the surface. Blue means they're about 2.5 meters below the surface. So everywhere you see these colored dots are potentially locations where crew could dig a trench to see if there's water ice. They could drill to see if there's water ice. And if they can uncover it, actually maybe measure the composition of that water ice as opposed to trying to bring that very delicate water ice all the way back to Earth. It's much easier for them to bring rocks back than it is to bring ices back. So most ice analyses will likely need to be done in situ, at least for the first several years. It's also possible that they can do a survey of the subsurface. So if they have certain instruments like a ground penetrating radar or a neutron spectrometer, they can walk across the surface or potentially drive across the surface and survey the subsurface as opposed to taking point measurements or digging isolated, localized trenches. Okay, so let's take a little closer look now at the surface as it exists as a geological surface. This again is Shackleton. There's the South Pole. There's this wonderful ridge right here. And this is an oblique view of that. Again, you can see the shadowed interior. South Pole is over here. There's that ridge that I keep pointing to. And this is the impact ejecta. You can see it very nicely over here. It looks very much like the material outside of Meteor Crater. Now let's fly towards Shackleton Crater and a potential landing site at the South Pole. This is contoured to give you a sense of the topography. There's Shackleton. And right here is the South Pole. These blue patches are areas that are in permanent shadow that might have caches of water ice. Okay, so let's imagine they land right there at the South Pole, not just at the ridge. Okay, there's the South Pole there. This is the interior wall of the crater. There's the South Pole, and you can see there's all kinds of little pockets, some of which are going to be in permanently shadowed. So within a few hundred meters of the South Pole, if they landed there, potentially they could make some measurements of volatiles. As I said earlier, these small caches of volatiles are going to be very young, and therefore, if there are volatiles in them, they're more likely than not to be dominated by solar wind. So they'll be similar to the samples collected by Apollo 16 and Apollo 17 astronauts. Here's an example of one of those shadowed rock areas. So here we have this wonderful boulder complex, and it's casting the shadow. And so this is the type of thing that a crew could go into and trench or drill to test our volatile models. There is also some wonderful boulders in that ejecta that was excavated from Shackleton Crater. And these boulders are much larger than anything the Apollo astronauts saw. Some of these boulders are going to be excavated from 4 kilometers beneath the surface by Shackleton. Some of these materials we think were lofted up towards the surface by that immense South Pole Aiken Basin impactor, that 2,500 kilometer beast that is just north of the South Pole. And so this material here is likely nothing like anything we saw at Apollo. It could be some of the oldest crust of the moon that we've ever sampled. So that's going to be very, very exciting. Okay, so they're probably going to collect some rocks. And I know some of you are saying, oh, more gray rocks, right? Okay, more gray rocks. But this is, of course, the stuff that produces all those big ideas that I showed you in that second chart, okay? And I know that they're not as glamorous as footprints and flags, but I tell you what, if you are a scientist like me and you get to study them in the laboratory, you find out that they're actually pretty nifty and colorful. This is what these samples look like once you prepare them and put them on a microscope. This is an Apollo 12 basalt that is just beautiful like stained glass. Here is a sample from Apollo 17. This, by the way, contains the mineral ilmenite. This is rich in titanium. This is another one of the resources that we might go after once we're finished exploring the South Pole. This type of material you can process with hydrogen or carbon and extract water. You can react it with the hydrogen extract the oxygen and produce water. In fact, there is an instrument down at the Johnson Space Center that will literally do this, and you can watch drops of water fall off the instrument. It's really spectacular. And here is a sample of an impact, a sample affected by impact. This is also from Apollo 17, and these are the types of things that we could and hope to see at Shackleton Crater. Okay, so let's now talk about what the crew might have to overcome. Okay, this is a topographically complex area. I've said that many, many times. Here's our South Pole. This is now contoured in 100-meter intervals. Okay, so and again, I want to say this over, and I'm going to say this over and over again. The precise landing site's not been selected. Okay, somewhere in the South Pole area. But let's, for the moment, say it's at the South Pole, and let's, for the moment, say that the crew have no mobility. So it is a walking EVA, okay, just like Apollo. Okay, we in fact were asked last July to evaluate this. NASA headquarters called us up and says, okay, if they land at the South Pole and they walk 2 kilometers, what is it they're going to be able to do and see? Okay, and so we identified some of those boulders I showed you in some of the earlier slides, but we also pointed out the topographical challenge. Okay, if an EVA from the South Pole along the rim towards the lower left quadrant occurs, that requires a climb about 140 meters over that 2 kilometers. Okay, in a spacesuit, that is not a trivial task. If crew continues along the rim crest, then an elevation change of 470 meters is required. And if you go all the way out to this ridge, that's 600 meters. Okay, so there is going to be some topographical challenges if there is no mobility assistance. Okay, so I've long argued, and I hope this will prove to be the case, that we're going to provide them a mobility asset. Okay, it may be an unpressurized rover with the first mission, but we want to get them one of these pressurized vehicles just as soon as we can. This is the terrestrial prototype. This is called the Lunar Electric Rover. We had 2 of these. We tested these in northern Arizona in 28-day long mission simulation, simulating actually a mission to the South Polar region of the moon. These are wonderful vehicles, and these actually have the potential of taking astronauts a full 100 kilometers from any particular landing site. Okay, now I've been speaking about Artemis III, a single mission to a single destination, but Artemis is designed to be a program with a sequence of humans to the surface missions. And NASA hasn't outlined any particular plan, but they have, working with their international partners, other space agencies, such as the European Space Agency, put together what they call a design reference mission. Okay? This design reference mission has 5 landing sites, and the way it works is, in this design reference mission, 2 of these rovers are deployed at Malapert Massif. Once they're safely on the ground, 4 astronauts are launched. They land there, 2 go in each rover, and they explore the area for 42 days, come back to Earth with a bucket full of samples. Then Houston telerobotically drives those rovers to the South Pole Shackleton Crater. The second set of astronauts are launched, land, conduct another 42-day mission. They come back. Houston telerobotically drives the rovers to the 3rd landing site in the Schrodinger Basin, and so on to Antony Crater and SPA Basin, so 5 landing sites. Now, with the current Artemis III program, we're going to do this first, and then there will have to be some discussion if we were going to go to Malapert, or we're going to go down to Schrodinger, or somewhere else. But this allows us to evaluate the requirements that the equipment, the hardware will need, and what requirements that puts on crew, what requirements that puts on operational support here on Earth. So it's been a very good exercise to actually map out this particular sequence. And in fact, we have discovered smart things that we would not have anticipated without doing this type of trade study. Okay? So for example, we realize that we can actually put instruments on the Lunar Electric Rover. And in fact, we did. We put a ground-penetrating radar under the aft deck of this rover, and we took it out to Arizona and we drove it around in one of these mission simulations to see if it operated over those rather rough conditions and could successfully image the subsurface of the Earth as a proxy for imaging the subsurface of the Moon, and that worked just fine. And so now we realize that while we are telerobotically driving the empty vehicles from one landing site to another landing site, we can use them to prospect, okay? So here is Shackleton Crater, here's Schrodinger Basin. So these are two of the landing sites in that design reference mission. We have a crew mission here, then we telerobotically drive the rovers down to Schrodinger. Well, as it turns out, you can actually get to Schrodinger in like 3 months, 3.5 months, okay? These missions are scheduled to be launched on a cadence of a year. Okay, so we have a lot of extra time, and so the idea is we can detour over here to Amundsen Crater, which has an immense PSR and may have vast quantities of water ice, and survey it. So here's the PSR in this region here. This is where we've calculated water ice will be stable. This green area is where we've calculated dry ice would be stable. And so you can drive the rovers in and out, in and out, in and out, and do a zigzag survey prospecting for subsurface water ice over an immense area in between crew landings, okay? And this is the type of thing that never would have occurred to us until we did this type of analysis in this design reference mission. Okay, so the one thing I should say, because it's kind of a local pat on the back, this Lunar Electric Rover was built. This is a terrestrial prototype. The Generation 1 vehicle is what we call it. It's been tested in 3-day, 14-day, and 28-day mission simulations to the Moon. That 28-day mission was specifically for a mission near the lunar South Pole. Tests include more than 1,100 hours of astronaut time in the vehicle and nearly 3,000 hours of total crew time in a high-fidelity simulations. And traverse studies recently published, well, about a year ago, indicate that routes between the 5 sites that I've highlighted here are feasible in this type of vehicle, okay? So this was built down the street, if you will, at the Johnson Space Center, and I hope that they get the green light to build something like this for our Artemis crews. Okay, so this is my summary slide, and then I'm going to take 3 more minutes for a short video. So just some 40,000 foot level type of bullets. We should, I think, explore the unexplored, and that means go to the lunar far side and the poles, which the Vice President has directed us to do. I think that we need to land on the surface, not just orbit the Moon or fly by the Moon. We learned from Apollo that to make truly transformative scientific discoveries, we need sample return missions to high priority landing sites. South Pole being one of those, the Schrodinger Basin being another. And although I spent no time on this because of time, an integrated robotic and human exploration program with international and commercial partners will, in the end, produce the best program, okay? So if you'll give me just a second, I'm going to bail out of this PowerPoint and show you a 3-minute video that we produced. And let me say a few things about this video. We put together this video to kind of inspire the public, inspire the scientific community, inspire the engineering community. It is assembled from relatively recent imagery from the Lunar Reconnaissance Orbiter, which is currently in orbit around the Moon. But in a few places, we have put together a quilt, a patchwork of those new images on top of old Apollo era images so that you can get a sense of how sharp our rendering of the lunar surface is relative to what it was in Apollo. Okay, so let me get out of this. Okay. Okay, David, I take some questions now.